Right, so the main point that I wanted to make here is that this data that these models are trained on is incredibly powerful. It has a representation of our world and how humans interact with each other and create. And basically, you can think about foundation models as the best statistical model to absorb all that data. So it's just the best sponge that we have to absorb human knowledge. And so it's incredibly powerful. And now you're putting that on a robot head. And so obviously, it's going to change the way the capabilities of the robot to understand its environment, to understand humans, to respond in a way that may feel more creative because it now understands how to create human content. Cool. And so, yeah, maybe this is redundant, and since we have some technical difficulties, I'll move through it quickly. These models are, yeah, very powerful. They can do common sense reasoning. They can answer questions in many college level subjects, write code, which is very important for robotics. They can, if you look at the multimodal ones, they can now read like your kid's homework and not only read the machine text, but also the handwritten text and the little drawing that your kid made, and actually answer the question, is this physics problem solved correctly? And if not, then answer how it should be solved and do all of that. So, and multimodal foundation models have now grown to also use audio and video. So they are basically, it can understand the real world and answer questions about it. And one important concept of foundation models is this in-context learning capability, which is something that emerges when they're large enough. So this was introduced in GPT-3, and this is what people know as prompting. So essentially, instead of, normally you take a machine learning model and you want to adapt it to a new concept, and what you do is that you take a bunch of data, label it with humans, and then fine-tune your model, and you need compute. It's pretty painful. And within context learning, all you need to do is just give it a few input-output examples of how you want to use this model in a new way, and it actually can understand that pattern and apply that pattern in a new context. And so that's incredibly powerful because then now you don't need massive amounts of data to modify this model. And in many, many applications, this has achieved state-of-the-art compared to like specialized models for that task, which was why people were so blown away by the power of these models. And an important concept to note too is that this amount of information you can put in this for context learning is called the context window. And this context window has actually dramatically increased over time. So the latest was the Gemini 1.5 Pro context window, which has 1 million tokens, which essentially means that you can feed it an entire book or like an hour video. And with that, you can modify the behavior. And so you can think about the context window as your short-term memory for the model. So obviously, the longer that is, the more context the model will have in order to answer your questions. And in a lot of the work that I'm going to present, all we're doing is taking LLMs and using in context learning to modify their behavior for us. And we also have some work in which we're modifying the LLM itself, but I'll point that out when it comes. So what that has done is that it created like a different context for robotics, especially in the context of human-robot interaction and building more social robots. Starting with, this is some of the work that we've done in the lab. So starting with, robots can understand language, right? They can reason in context. They can hold a situated conversation about something that's happening in this room. I'll go over some of these examples today. Importantly, these VLMs can also be adapted to produce robot actions. And I think what's most interesting about this is that it brings the generalization, the visual language, semantic generalization onto actions. So now you can, for example, ask the robot to move something to the Taylor Swift picture. And even though Taylor Swift was never in the robotics data, it understands that because it's transferring that information from the VLM. And then the last one is actually more recent that we've been working about is how do we get humans to teach robots new behavior, whether it's high level or low level. And this is also enabled by foundation models. So I'll also explain some examples of that. Okay, so let's start with the first one. This is what most people, I've seen actually a lot of people using this in this conference. So it's essentially you just take the LLM and you use it as your task planner. LLMs, of course, understand natural language. So if you say, I spilled my drink, can you help? That's actually pretty an interesting query from the semantics perspective. You have to know what it means to spill a drink and what the robot is expecting when he says, what the human is expecting when he says, can you help? And typically this was very hard to do, but now an LLM can just tell you semantically meaningful things to do. And the main challenge you're going to have is these LLMs are not grounded. They don't know the capabilities of the robot. They don't know what's in that environment. Keep in mind, right now we're talking about just language, so there's not even vision here. So what we did, this was a couple years ago, was simply combine the LLM produce output with some scoring functions from the robot policies. And when you combine the two, you can ground it. And now you can, for example, pick the most likely thing the robot can complete that is also semantically meaningful. In this case, it decides to pick up a sponge. And you do that repeatedly, and you can get the robot to do like 20 different steps for something that feels sort of ambiguous when it was first described. So it works something like this. If you say, I still might drink, can you help? Then it pulls up an LLM. It identifies all the key things that it could do. Then it actually goes around the room, understands what's in the room, and then it pulls up the policies and scores each one of those options. And then it will pick the one that it can physically do, but was already offered as a semantically meaningful next step to do by the LLM. So that's how it works. So that's SIHR. There's a lot has happened since then. PaulMe was the next advance. PaulMe was a significant improvement because it was actually using the sensors from the robot to make the decisions. So now you're interleaving images and natural language requests and outputting natural language output on the next step. So it's still sequencing of tasks, but now it has the sensor input. So if you look at just the one on the bottom left, we're asking the robot to like pick up a bag of chips, and then normally SIHR would do this, but now the human can mess with the environment and the robot will keep retrying because it's understanding that semantically the task is not complete and it has the visual input and it can decide to continue to do that task. In the one in the middle, you can do really interesting things. So in this case, it was just saying put all the blocks of the same color in the different corners, and that was all. But it can also do things like make me a smiley face with a red mouth. And it like just takes the visual input and it can keep moving the blocks until it feels like it semantically has the right expected image. The other thing that we have done, and I know many people ask me all the time about how do we make sure these LLMs are not just going off and doing crazy things. An important thing is to figure out how we can get the LLMs to ask for help or to understand what they don't know. And so this work called Robot Help was exactly about that. Normally in the previous work, if you just ask the robot, hey, bring me a soda, it would actually go to the soda to the table and pick up the one that's closest because it's the easiest to pick up. But it's probably an ambiguous request, and you wanted to instead say, okay, which one do you want? Or do you want it cold? Like there's more questions to be asked here. So how do we incorporate that? In this work, what we did is that we took the same approach of doing SIHR or PaulMe and create a sequence of steps. So that's this thing right here. I don't know if you can see my cursor. And then we just added a single step called conformal prediction. It's just a statistical approach that allows you to extract from a set of options the minimal set that actually contains the right option with a very high probability. And that typically returns the correct answer. And if instead it actually returns more than one answer, it indicates some ambiguity in the set, and therefore it's probably a good candidate to ask for help. And so in this case, whenever conformal prediction returns a set larger than one, we just ask for help. So it looks something like this. So if you ask the robot, hey, can you bring me a ball? In this case, there's a plastic and a metal ball, and it decides to ask the human what to do. And then the human can respond, oh, I want you to do the plastic ball. And in this case, it's the right thing to do, especially because it's going to put it on the microwave. So that's an example of how you integrate human feedback into these planners. And this is actually a new project that we actually put out last week. And the idea is, can we leverage LLMs to do navigation? So not only to talk back and do planning, but also to help you navigate. And the idea is that you could just show up to your robot and be like, hey, I have this bucket of toys, where can I put it? And the robot understands your building, and then it tells you where to put it. And it's a very semantically interesting query. And what we do is we simply, this is just the robot executing the action, bringing it to the toy box. So what we do is that we essentially just give the robot a quick demonstration tour. So there's no map generation, there's no map building prior to this. It's simply you give it a tour, takes video input, and then at runtime, you just come and ask it a question. And that question can be multimodal because it's leveraging a VLM to actually answer that question. And what it does is that it answers the question, and it also takes you to the place where you want to do it. This is a very, very simplified approach that actually doesn't require LiDAR. There's no pre-creation of a map. It is very low on compute, and it works across embodiments because at the time of navigation, it's just using whatever MPC approach you have on the robot, whatever navigation policy you have on the robot. And the way it works, I'm going to just do this very briefly, is that when you're doing the entire video recording, you're actually putting that entire video in that context window. This is using the Gemini 1.5 Pro model. So you're loading that entire video, which in this case was, I think, 20 minutes for an entire floor. And then in parallel, you're also building, using structure from motion, a topological graph, which is essentially just is a graph with a bunch of nodes that are just images. And then you take, when you ask the question, hey, robot, where should I put this bucket? What you're doing is you're actually asking Gemini where in that entire video sequence you saw something that might be relevant to this question. And Gemini will return essentially a frame that it saw the video, and that frame is associated with the closest map in that topological graph. And the robot just knows how to navigate to that topological graph. It just does pathfinding and visual localization in this case. So it's extremely simple, and we were surprised, frankly, that it works so well. Okay, so those are all examples where we're using the LLM or the VLM at the very high level, and low level, you're using whatever other policies you had there. We also have a lot of work where we actually modify the VLM to actually work for actions. And there's a couple ways to do that. This set of work, I won't go into this because this will take an hour, but this essentially work where we take the VLMs and we fine tune them for actions. And that means that the VLM speaks a new language, and that new language is actually the positionings of the robot over time. So this is actually the VLM physically moving the robot. So I figured that wouldn't be as interesting in this audience, but it's certainly interesting because it brings generalization to actions. So let me give you a couple examples. So now a single model, you can just talk to it and ask it, move Cocan to Taylor Swift, and it's just going to move it to Taylor Swift, even though that data that we added to adjust the VLM never had Taylor Swift on it. It just had examples of moving Cocans. And so, or similarly, you can say, move the banana to the sum of 2 plus 1, and there's one page there that has the number 3 written by hand, and it also understands that. So that's the kind of generalization that it brings to the action models. The other way to bring this to actions is through code as policy. So this was actually from 2023, and essentially, these models are extremely good at writing code because there's so much code in the internet. And so all we did was, again, prompt it in order to modify it to run robot code. And we gave it example, for example, control APIs and perception APIs, and told it it could use those APIs. And if you think about all the work I talked about earlier, what you were doing there was just sequencing a bunch of tasks. In here, you're not only sequencing, you're writing control structures, you're writing hierarchical functions. So it's strictly a more powerful way of using VLMs. And so if you do that, you can actually just do much more complex things like draw that 5-centimeter hexagon in the middle. Basically, it starts writing code that leverages external libraries to do math and geometry, for example. Cool. And I want to have some time to talk about this. So this is more recent, and it's essentially how do we leverage VLMs to teach robots? And I think this is important because, as I mentioned, there's no robot that's going to become perfect to operate in your home or in whatever environment you're in. You're going to have to modify its behavior, and it's important that you can modify it in a way that is intuitive. So I thought this was relevant. So what I mean by here is how do we teach robots to change their behavior? So here's just one example. This was presented at HRI earlier this year. And this is our student Karthik, who basically was visiting, and he said, I want to make the robot do expressive behaviors. And by expressive, you mean just like any of these expressive behaviors that usually animators can build in. And he wanted to teach the robot to acknowledge that a person was walking by, but he didn't want the robot to speak every time someone would come in, because there was constantly people coming into the kitchen. And so what he did is he leveraged LLMs in two ways. The first thing is that he actually asked the LLM, hey, if I want you to acknowledge a person, how would a human do that? And so the LLM obviously can retrieve that pretty simply. And then, again, just modifying within context learning, we can get it to also translate it to what a robot should do, given what humans do and the APIs on this robot, what should this robot do? And it basically translates it into a potential way of greeting people. And then it can do code generation just as in code as policies. And in this case, it decided that the best behavior was to look at a human, nod his head, and then turn the lights green. And this is something that it just came up with, given the APIs that it was given. And the cool thing is that it doesn't stop there. You can continue to have this interaction with the robot and just say, oh, I actually want you to make sure you keep looking at the person as they walk away. And then this entire loop just replays, and then the behavior gets modified. And all we have here is just a set of APIs to do basic behaviors and the natural language interface. And the human can modify the robot behavior using that. So doing this, you can teach it to do things like attention. So you can see, for example, the robot just came and looks at the object, and eventually he nods to show that he's paying attention. This was just Karthik playing around to see what behaviors he could teach. He also showed him how to do this disappointment and confusion. I'm not sure confusion is very clear. It's very confusing. You're like, what? Okay. So that was his interpretation of confusion. Cool. So that's basically use an LLM to understand what a human might want and translate it into code. What if you wanted to teach it like a very low-level behavior? What if you wanted to have a quadruped and teach it how to give you a high five with both paws or one? That feels like a very low-level behavior. So we have actually many different threads trying to do LLM to low-level actions, and it's actually very hard. And one of the key things that we're trying to answer is what is the right level of abstraction to interface an LLM and a low-level control. And we have tried code, as you've seen. The other things that we are exploring is reward functions or even predicting motion trajectories directly. For quadrupeds, you need something that will work at very high frequency. So in this work, we actually use reward functions. You might ask why. So a reward function looks kind of like a mathematical equation or like code, and it essentially is capable of representing a very wide range of behaviors. It's certainly used in locomotion all the time for reinforcement learning. It's also used for many of the trajectory optimization algorithms, and it's semantically rich, certainly something that an LLM should be able to write. And there's just a rich literature in how to translate reward functions to high-speed, low-level control. So we tried this, and once you have the reward function, in this case, what we used was a trajectory optimization algorithm in Mujoko called MJPC. So we were teaching robots in simulation through interaction. So let me show you what it looks like. Here, a person was trying to teach a robot to give it a high five. So what's happening here is when you speak, the robot writes this reward function, and then Mujoko is using trajectory optimization algorithm MJPC in order to actually find the right action sequence to maximize this reward, and that translates into the behavior that the robot has right there. And then once it does the behavior, you can actually click, yes, that's what I wanted, no, that's not what I wanted. And you don't need to read the code. The code is there simply for demonstration. In fact, when we tried this, we were using, so that's basically the behavior you want right there. When we tried this, we actually got a bunch of people that were not team members, that did not know how to code, and asked them to interact with the robot and teach it new behaviors. And that's how we came up with this entire setup. And it also works on the robot, importantly. So what we found out is that you can deploy the trajectories that are created by MJPC directly, because you need very high frequency feedback, and you also need like perfect state estimation. So instead, what we did is that we did a whole lot of trajectory generation in simulation, and then we distill it into a policy that is essentially a small transformer policy that gets put on the robot. Long story short, you can definitely get a policy that is language conditioned on a quadruped to teach it something completely new, and something that feels like you can describe it in a very semantically meaningful way without telling it positions or anything like that. So this is an example of an interaction. And I actually have a video at the end if you want to see it. I think that would be the best. Cool. And then I have one more. I don't know how I'm doing with time, but let me know. One more is language model predictive control. This was actually presented earlier today in the session. The idea is, imagine, let me play that animation again. Imagine that during the day, you're teaching the robot using this interactive method a new task. So you're teaching it to do, like, I don't know, push all my toys to the right, or I want you to walk and enter the room in this way. And what you do is during the day, you accumulate all these interactions. And imagine now that when you go to bed, the robot also goes to sleep and it takes all of these interactions and absorbs them into the LLM that is actually creating the behaviors. By absorbing them, I mean you actually use the interactions to fine tune the weight of the LLM that is generating the behaviors. And what happens is that the next day, the robot is simply better at understanding what you mean when you say, move closer to me, better understanding how to write code based on the interaction. And I'll show you how that works. So the interaction looks kind of like the one on the left. You just talk to it, you write some code, you look at the behavior, you're like, no, that's not what I want. Then you keep interacting until it actually does it at the end. And then we have a button at the end that says, yes, you did it right. And then, so this distribution here is what happens the very first time you interact with this LLM. You did nothing other than gave it a couple examples within context learning to get it to produce reward functions. Then after fine tuning, actually the distribution of performance is significantly up and to the right. And up and to the right just means that it has higher performance with fewer interactions. And I'll show you actually, I think I have in the next slide. But this is the general idea that we're basically teaching the robot in two ways. We're doing in context learning to essentially get it to memorize new behavior patterns. And then you use all of that interactivity to give it as a buffer of data to train at night. And you basically do model fine tuning at night. So it's probably can be interpreted as a version of like short-term learning versus long-term learning. And the performance is pretty drastic difference. So the bottom line on the right is essentially what happens if you just do some prompting of your LLM. You're probably going to be very frustrated most of the time because it gets you about 30% success after interacting with the robot. But after fine tuning, it actually learns quite a bit how to interact with people. And you can get up to 70% in just like 3 interactions, which is pretty cool. If we have time, I'll play this video. I know we had lots of technical difficulties. Ah, okay. This is an example of somebody teaching. So, I mean, I'm gonna stop the audio, but you can see that he's basically interacting with it. It actually writes some reward functions. It sees the behavior. He can push it to the robot, and you'll see that he's speaking completely naturally. Like we try to rehearse this, there's no way to rehearse it. You just speak whatever makes sense given the behavior of the robot. And so you will see that towards the end, he essentially teaches the robot. This entire video was 4 minutes. And he just basically teaches the robot to open the door at the end. And then the cool thing is that you can combine it with all other behaviors and just build multiple behaviors over time. And then the robot essentially becomes a robot that is unique to you because only you have taught it that kind of sequence. So in this case, it's going to do that. Right. So you can see that you can definitely continue iteratively continue to improve the behavior of the robot, and also the underlying models can actually improve the more you interact with it. I think that's it. If you have any questions, happy to take them.
Thank you. I think we have time for one or two questions. Any questions from the audience?
There's a question online. So a question, have you looked into interaction with more than one person, so like in a social context?
Yeah, actually, no. We have not done interaction in a group, but that would be very interesting. Yeah, most of the time we've been just trying to get a single person to modify robot behavior.
Yes.
So that's the extent so far. Yeah, great area to be extending it into.
Yeah.
Great stuff. Would you be using foundation models also for some kind of ethical, moral safekeeping? Like, don't do that with the foundation models?
Yeah, we get that question a lot. I mean, today we don't, but the answer is we are working on it. Definitely, there's a lot of, and I would not consider it the only way to keep safety on robots. I would consider it as an additional layer because it's so much easier to basically specify some rules that are just semantically easier to specify. But if you had to make an exact rule, you're probably going to miss a lot of cases. So yeah, we're working on that.
So like mobility behavior or whatever you call it, the mobility vision. So you have a foundation model, then you also have like a bunch of different other things like navigation. Are they like also networks or are they kind of classical navigation?
So basically the pathfinding, localization, and the actual navigation is NPC. So those are the classical things. And all of that we have differently is that we're doing this like connection of the entire video sequence. Well, first of all, we're using a VLM like Gemini to be able to answer the semantic question and identify where in the video it is, and then do a mapping from that to the topological graph. That's the only thing that we're adding to an existing system.
Right. Okay. So my real question is like, so what stops you from really learning these graphs and localization from the foundation model itself?
Yeah, I mean, you could. We also have work where we're doing like visual navigation, but yeah, it's completely something that you can add. There's nothing stopping us from that. Yeah, we have work on that as well.